next session is in an invited talk by Yael Kalai. I think for this audience, I probably shouldn't need to introduce Yael, but let me do it anyway for those of you who don't know her. So she's a professor at MIT. You may have heard of a little thing called a ring signature. Like that would be kind of something that she gave us. In fact, she's so accomplished, she won an ACM prize for computing. For many of you in the room, what will probably be the most important bit of information, he's currently program co-chair of crypto. So Yael is judging you harshly right now. So without further ado, Yael, the stage is yours.
Hi, thank you very much for inviting me. I'm super happy to be here. I have to say, so I'm going to talk to you a little bit about succinct proofs and kind of their interplay between theory and practice. And I have to say that when Martin and Nick sent me an email saying, we would like to invite you to give a talk at Real World Crypto, you know, I read this line and I was thinking to myself, like, is this a joke? And why was I thinking that? Because, you know, I kind of tend to live on the cloud, playing around with math and theoretical computer science. And of course, this conference is all about the real world. And thinking to myself, what do I have to do with the real world? Actually, I'm really trying to avoid this real world in any way I can. But actually, after reflecting on this for a bit, I'm thrilled to stand here and speak. And because I really think, while I do enjoy living in the clouds in my ideal world, I do think that this interplay between theory and practice is extremely important. And what I want to do today is tell you a little bit about my journey and kind of my own kind of interplay, how I interplay between theory and practice. And in particular, I want to tell you about my journey when kind of thinking about succinct proofs. So first, before I start, let me say, like every journey, the best part of the journey is the people who take the journey with you. So I just want to spend a second acknowledging my amazing, amazing collaborators, students, postdocs, and colleagues who made this journey kind of the best ever. Thank you. And actually, my journey started as a grad student when I learned about kind of the evolution of proofs in computer science. So let me spend like 5-10 minutes telling you a little bit about this in a nutshell, because it's just so beautiful that, you know, I would like you to know about it. So, you know, classical proofs have been studied for thousands of years, starting in ancient Greece, and it's a, you know, well-studied branch in mathematics until today. And a proof is typically, when people think about proof, they think a long kind of, you know, pages of pages, and you kind of read and verify it line by line. It's kind of a bunch of logical deductions. That's what a proof is. And that's what a proof was and still is for thousands of years. And this changed in the mid-'80s with the notion of interactive proofs, which was also kind of motivated by the concept of zero knowledge, which I'm not going to get into. But what is an interactive proof? As opposed to just pages and pages of proof, now a proof is an interactive process. It's actually a conversation between a prover and a verifier. And the verifier, crucially, tosses coins. He's probabilistic. And there's some probability of error. So the only guarantee is that a false statement, it may be accepted, but with negligible probability. So you can make this probability kind of go to zero. So practically it's zero. But there is still a slight probability that the verifier will accept a false statement. Turns out that by relaxing proofs to be probabilistic and interactive, turns out that these proofs are much more powerful. In particular, what was shown is that the time that there exists an interactive proof for any kind of statement where the verifier's runtime is essentially like the space required to do the computation. And this is kind of Shamir's celebrated result, which is known as IP equal P space. So any language in P space, there exists an interactive proof for proving it where the verifier is polynomial time. Wow. Okay. So whereas with classical proof, we can do what's called, we can do NP. With interactive proof, we can do P space, much bigger class. Wow, very powerful. Shortly after interactive proofs were introduced, multi-prover interactive proofs were introduced, also for the sake of zero knowledge, getting this time information theoretical zero knowledge. But what are multi-prover interactive proofs? So here we have two provers, okay? And we have a verifier, probabilistic verifier. The verifier sends queries, questions to these provers, gets answers. So, and importantly, it is assumed that these two provers do not interact. So these two provers are put in separate rooms, okay, with no interaction. Turns out that this proof system is extremely powerful. In particular, any proof, classical proof, can be made exponentially shorter using a two-prover interactive proof. And if you think about it, why is it so powerful? Like, how can any, and by the way, this is called the celebrated MIP equals next, MIP for multi-proof interactive proof equal next. Because for polynomial time verifier, he can be verified of any statement in non-deterministic exponential time. Now, intuitively, why is it so powerful? Intuitively, it's because you can think of the two provers as kind of two different suspects. It's much harder to cheat when there's two suspects, and they're kind of in different rooms, and now they need to cheat consistently. And indeed, this interactive proofs really what they use is kind of a bunch of consistency checks to catch these cheating provers. Okay, so this is very powerful. And now listen to this. Here's the next observation, a very simple observation due to Faulkner, Rumpel, and Zipser, is the following. Well, if the communication is so small, so if a proof of size t, now the communication, then the size of queries and answers is like log t, because it's exponentially shorter, their observation is actually, forget about the provers. Ask prover one to kind of write down the answers to each and every possible query that he could have been questioned. And he'll put all the answers to each and every possible query that he could have received from the verifier. Similarly, prover two, we don't want to interact with you, just put in the sky, like give me this long list of every possible answer that you may, for any query that you may have gotten from the verifier. And now basically, you can think of kind of all these answers as one big proof that the verifier verifies by randomly choosing kind of two cells in this proof and only reading them, the answers in these two cells. Wow. And this led to this really celebrated and beautiful PCP theorem that actually says any proof can be converted into one that the verifier can verify by reading 3 bits of the proof. And he's convinced with probability 7/8. So of course, the cheating prover may be lucky, but with probability, he'll catch him with probability 7/8. And you can repeat it to amplify the soundness. I find this amazing. So this is what I learned as a grad student. And I remember thinking, wow, beautiful. So this is kind of the evolution of proofs, classical and proofs, IP, MIP, PCP. Since there's a lot more. When I was a grad student, I remember Eli Ben Sasson was a postdoc with Madhusudan, and he was studying PCPs at the time. I remember once we were sitting in the lounge at MIT, and we were talking, a bunch of us from theory and more practical people, and they started challenging Eli, who was really deep into these PCPs, telling him, we don't understand, what motivates you? I mean, come on, nobody's ever going to use these things. They're so inefficient. There's no way they're ever going to be practical. And I remember Eli kind of, really trying to get out, like struggling to give a good answer. Basically, if I remember correctly, the answer he gave was something like, oh, come on, this is so beautiful, beautiful and simple, like beautiful ideas will eventually find use, or something like that. And of course, people were like giggling and laughing, like, oh, come on, there's no way, no way, no way. And as many of us know today, so now Eli is giggling, he's happy. And a couple of years ago, his company with Ale and others were evaluated to be worth $8 billion using PCP technology. So, I want to emphasize that I think really beautiful ideas, I agree with Eli, tend to have, applications in practice. And what we need to do is to be able to talk about them and learn from each other in order for this to happen. And I want to say, I understand why the giggling at that time, where it came from. Because at that time, all this theory of interactive proofs, or MIP or PCP, all the work on proof systems was really with a theoretical viewpoint. And really the way we thought about it as the verifier is efficient meaning polynomial time. That, for theorists, that's the definition of efficient, polynomial time. The prover, all powerful. We don't care about the runtime of the prover. What can we prove to an efficient polynomial time verifier? And even in one of the papers, we referred to the prover as a Merlin, a wizard. Like he's all powerful. Now, of course, in the real world, there is no all powerful, as we all know. So of course, this is theoretical work which will never be used. And let me even say, even if you look at the IP equals P space theorem, the prover there, not only it wasn't, no one cared about its runtime, it was really inefficient. If you look and try to compute the prover's runtime, you'll see it's like 2 to the space squared. So it is grossly inefficient. Now again, that wasn't the emphasis. Okay, so at that time, the emphasis was to get a polynomial time verifier. What can be proved a polynomial time verifier? So together with Shafi and Guy Rothblum, we started talking about what about a doubly efficient interactive proof? This was kind of towards the end of my PhD and also during my postdoc. But thinking about kind of making this closer to being, ever have any chance of ever being used, of course you want a proof system where the verifier should be very efficient, so it should be very easy to verify the proof, but also the prover is not all powerful. So when we say doubly efficient, we mean also the prover should be somewhat efficient. And by somewhat efficient, what we want to say is that a prover can prove the correctness of a time t computation while running in time not much larger than t. Okay, so what do I mean by not much larger? Ideally, linear in t, quasi-linear in t, polynomial in t, ideally as close as possible so we can actually use these things. Okay, we defined it at that point, remember, to be polynomial in t, okay, but not exponential in t. Now, do we have such a thing? How can we prove, how can we have an interactive proof where both the verifier is very efficient and also the prover is efficient? So we came up with such a interactive proof for low depth computations. And let me tell you the gist of it, because it's really, the idea is extremely simple. So here's the basic idea. Say here's a circuit. Think of it as very shallow circuit. Okay, so it's a circuit with gates, ands, ors, for example. And let's say I'm a prover, and I want to prove to you that the output is 1. Your goal is to catch me if I'm cheating. How will you catch me? You'll say the following: well, I don't believe you. Give me the value of the 2 children. And you'll check that it's consistent with the gate, with the output 1. Now, if I cheated and the output was not 1, and the 2 children are consistent with the output being 1 of these 2 children must be false. I must cheat on one of the 2 children. So now you can guess which one I cheat on. Maybe you'll guess I cheat on the left one. Okay, then ask me, give me the two children of the left child. I'll give you the the value of the two children. You'll check consistency with the gate. And again, if I cheated, if the left child is indeed false, one of the children will be false. Guess which one. So maybe you'll guess the right is false. And we continue in this manner until we reach a leaf, an input, and the input the verifier knows. Super simple, prover extremely efficient. Everything is efficient and simple. What is the problem? The problem is, it's enough that the verifier guessed one time incorrectly and got a correct label, and now the prover can freely cheat and will be accepted. So in order for the verifier to actually catch the prover, he needs to guess each time correctly where kind of the misbehaving, where the false statement, where the false claim is. And that, he can guess with probability 2 to the minus the depth, which is extremely small. So no good. However, you can easily, maybe not that easily, but you can get around this by basically applying kind of an error correcting code to each layer of the circuit. Think of the circuit as layered. You apply an error correcting code, and what an error correcting code allows you to, what it gives you, that if there's one thing incorrect, almost everything is incorrect. That's the idea of an error correcting code. And now we do the exact same thing of kind of going from layer to layer, but on the encoding. So we say, well, if the output was false, we reduce it to a value in layer below, but not on the actual wires, but on the encoding of the wires. And we kind of go reduce wire kind of layer by layer until we reduce to a point in the error correcting code of the input. And that the verifier can check on his own. So that's really all it is. And now, of course, doing the reduction from layer to layer, because we're an error correcting code, it's not as simple. It involves what's called a sum check. But that's basically the idea of the GKR protocol. That's it. Great. So this is how, that's the interactive proof for low depth computation. Of course, kind of everything grows with the depth because we kind of go from layer to layer. There's interaction for each layer. So if it's very deep, it will result with a lot of interaction. Now, let me mention, in practice, usually when people want to do these succinct proofs, they want to do it for NP, not for a deterministic computation of low depth. So how does that relate to what we want to do today? So the idea is, it's okay, we can actually make it work for NP too. How do we make it work for NP? Well, instead of putting my input X in the leaf, I'll put the X and the witness. So I want to prove to you that X is in a language and I have a witness. We'll do the exact same thing, but now the input is X and a witness. And we do the exact same thing. But now, when we said the verifier can check on its own because he knows the input, now it doesn't know the input. Because we don't send W. W is large. We don't want to send W. W is like the actual proof, the non-succinct proof. We're trying to shrink W. So the verifier doesn't know W. So what do we do? So now, verifier cannot compute it. What do we do? The idea is the prover first sends some commitment of W, and then when they do the GKR protocol, when they reach the leaf, now the prover kind of reveals this commitment. Okay, so it needs to kind of reveal a point in the error correcting code of X and W. Now, in order to do that, you cannot use any commitment. You use what's called polynomial commitments. I don't want to get to it, but I just wanted to mention that these things are used also for NP, but once you do it for NP, it becomes kind of, that's where crypto comes in. When you do the GKR for just bounded depth computation, there was no crypto, just algebra, error correcting codes, just pure algebra, no cryptography at all. When you go for NP, now there's a commitment, there's a succinct commitment, actually a polynomial commitment, whatever that is, and now crypto comes in. So it becomes from a proof to an argument. Argument meaning computationally sound proof. Okay, so I just want to emphasize that this succinct interactive argument for NP is interactive. There's a lot of rounds of interaction, like the depth of the circuit, as I mentioned. In practice, usually people want non-interactive arguments. Okay, they want succinct non-interactive arguments known as SNARGs. How do we get non-interactive arguments? Well, it turns out that the interactive argument that I showed you, GKR, is public coin. The verifier's messages are just random, random bits. So we can apply the Fiat-Shamir to it. Why not? So now let's kind of talk a little bit about the Fiat-Shamir paradigm and ask, well, is it secure? We want to apply Fiat-Shamir to this GKR protocol. Is it secure? Okay. In practice, yes, it's secure. It's used all over the place. ECDSA, which is, probably one of the most useful signatures, is based on this heuristic. And we use it all the time. Fiat-Shamir heuristic is used all the time. Never a problem in practice. Okay, so it seems like it's secure. But is it? There was no breach, but is it secure? Can we prove security of this? So, it's used all over the place. We should have an understanding of whether it's secure or not secure. So, yeah, I was Adi's student a while ago, and, I learned about this heuristic. I thought it was beautiful, very elegant, lovely, beautiful. And I wanted to impress Adi, and I said, I'm going to prove that it's secure. So I worked a lot to try to prove the security of this paradigm. And after working so hard and failing, I remember coming home one day, kind of feeling down that I've been working on this thing, no progress. I remember my dad telling me, well, maybe it's time to look for a counterexample. I'm like, no way, there's no counterexample. But actually, so there's a question, do we have a proof? Can we prove that it's always secure? Sorry. And the answer is no. Actually, there are contrived counterexamples where you start with an interactive protocol that's sound. When you apply Fiat-Shamir, it's not sound anymore. Now, does it mean that you should worry about using it? No, these are contrived examples, okay? But it still means don't try proving the Fiat-Shamir secure in general, because you won't succeed. So now, when is it secure then? So this kind of led us to believe, okay, we totally don't understand this paradigm. Because now we have a counterexample. So when is it secure, when is it not secure? So there's been a lot of work on this. And let me tell you, we know that for the GKR protocol, if you apply to the GKR protocol, we can apply it securely. Okay, again, I don't want to go into this paradigm and exactly how it's done, but let me just say, we can actually implement the Fiat-Shamir heuristic in a sound way, provably sound, under standard assumption, in particular, the learning with error assumption, which is not today one of our favorite assumptions because it's believed, or maybe somewhat believed, to be post-quantum secure. So we do have a proof for the GKR protocol. And just let me tell you, maybe in a word, I think we have, so we do believe that this paradigm is secure when applied to proofs, not to arguments, to proofs. When applied to arguments, it's shaky. We don't have a good understanding of what's going on there. Okay? Now, here's a result that just blew my mind. I just learned about it a couple months ago in Oberwolfach. So Ron Rothblum, we had a meeting, Ron Rothblum came and presented this work saying Fiat-Shamir, the GKR protocol, when applied to NP, like done in practice, it's actually when if you apply Fiat-Shamir to it, it's actually insecure. So actually he's like, here is a computation where you would want to apply, to run the GKR protocol on, and no matter how you try to instantiate the Fiat-Shamir on this, it will break down. But for NP, so for an argument. So that really blew my mind. He gave a talk, it was very insightful. And I want to say one thing about, so Ron, like me, he lives in the cloud. Okay, he's theory, in theory land. However, this year, I guess in the beginning of the year, he joined the real world and he works now at Succinct It's a blockchain company, and they implement GKR. Okay, and they hired him to do security analysis. And I think it is really kind of understanding how things are done in practice and kind of being a theorist, kind of observing, is what really led to this result. So this is kind of yet another example of how important this interplay, where theorists should come and talk to real world people, understand what's going on in the real world, to understand what's the right questions to ask. And people in the real world should try to tell us what's the right, what we should think about. And without this connection, our work as theorists becomes a bit irrelevant, and you don't get to enjoy, our fruits. So really, this interplay is, in my opinion, crucial and for the success of our field. So I want to say this kind of, in my opinion, this journey towards succinct proofs has been a real success story for theory of cryptography and cryptography at large. So as a perspective of a theorist, I can tell you we learned a lot from this process. There's been a lot of work done, a lot of connections between kind of other areas in theory. While working on this, connection to quantum physics, non-signaling, connection to hardness approximation, connections to the hardness of computing Nash equilibria, all these kind of very bizarre connections we found kind of during this journey. There's been a really nice interplay between theory and practice, where a lot of our schemes have been taken by more applied researchers and prototyped. And finally, from theory to deployment, today these things are used by various blockchain companies, Starkware being one of them, but now there's many others, most notably Ethereum, and others. I'm sure there's more I didn't write on the slide, but it's now starting to be used. And now we have kind of a joint effort with a bunch of us here called ZK Proofs. Actually, there was just a conference here in Sofia that just ended, I believe, yesterday on ZK Proof. And it's an effort to try to standardize these succinct proofs so it can be hopefully useful and easier to use in the future. Okay, thank you very much.
All right, we have time for a few questions.
Yeah, very clear talk. The one thing that wasn't clear, you said, I think, that the GKR is okay with Fiat Shamir for LWE. What's the LWE bit there? Can you
Yeah.
there a bit more detail?
Yeah. So what we managed to prove is that if you take this interactive GKR protocol and apply Fiat Shamir heuristic, there exists a hash function, a Fiat Shamir hash function, that if you use this specific hash function, then it's secure. And this hash function is kind of based on learning with error assumption. There's kind of a there's an LWE kind of thing. So we didn't prove that it's secure using SHA-256 or whatever people use today, but at least it's a proof of concept that if it's broken, the problem is in the hash function, because there are hash functions which are secure. I should say the hash function on which we proved security is not practical. So I'm not advocating to use that hash function, but at least it's a proof of concept that it should be secure. There are hash functions that are secure. If SHA-256 or whatever is not the right one, then dump that one and find another one. But there are hash functions for which the problem is not with the paradigm. So I guess my point is, if what we proved is if you use GKR today with Fiat Shamir and it's broken, the problem is that you use the wrong hash function. Because if you use the right hash function or a right hash function, it would be sound, unless you broke LWE. Thanks for the question, Nigel.
All right, I'm sorry we are out of time, so let's thank Yael again.
Thank you.